Thank you, everybody, for coming here this morning. It gives me great pleasure to have Davide here, who is actually professor at University of Zurich, as well as he is also a professor at ETH. And we will be here for a long time if I start listing all the awards and accomplishments Davide has. So and not take up all his talk time. So just a couple of things. Davide has done amazing work in visual inertial odometry, SLAM, and control for drones, and he's been doing some pioneering work with event cameras. I personally have been using SVO and SVO2 with great success. So thanks for saving me a lot of time, and as well as OCam Calib. And yeah, but without further ado, I'll let Davide just...
Okay, thank you, Dave, for the nice introduction and for inviting me here. It's really a pleasure to be here, also first time at MSR. So the title of this talk would be Robust Visual Inertial State Estimation from Frame to Event Cameras. Okay. And this is a picture of my group. So we are a group of 13 researchers with mechanical engineering, electrical, and computer science background. And the lab is fully funded by third-party funds. So also we have recently got a DARPA project about fast navigation with UAVs, and also some grants with the Intel and Qualcomm and the Google Faculty Research Awards. What do we do? So as they said, what we try to do is basically apply advanced computer vision algorithms to autonomous navigation of drones. So my PhD was about visual SLAM, visual inertial odometry for cars. But then in 2008, I started working on drones because actually they are more challenging than cars because they move in 6 DoF. They also have dynamic constraints that make them very difficult to control. And there are a lot of challenges, especially for perception. So that makes drones, for me, a very intriguing platform to work with. So we have 4 research areas in my group, which are the following ones. The first one is visual inertial state estimation, which will be most the topic of this talk. Then we try to apply these algorithms to autonomous navigation of drones. Here you can see a drone that is able to perform autonomously aggressive maneuvers, only using onboard perception and computing. We also work on deep learning-based navigation, where basically we try to do, at the moment, imitation learning in order to accomplish certain tasks. In this case, it was about following a trail in the forest autonomously using a forward-looking monocular camera. And then we have another area of research which is called event-based vision, which is about using a new class of cameras called event cameras that are almost 1,000,000 times faster than standard cameras. So half of this talk will be dedicated to this new research field because I consider it very revolutionary, I think, and that potentially will have a lot of impact in computer vision and robotics. I have a big motivation to build machines that can be used in search and rescue fields. So what we try to do in my lab is to actually work on autonomous navigation of drones, because what we want is that one day these machines can be used to search for survivors after an earthquake or a tsunami, for example. So in environments like this ones, for example, you cannot fly based on GPS because there is no GPS indoors. So you have to rely fully on onboard sensing and computing, but you also have to be fast because in the end, time will save people. So if you want me to give you a vision of what I would like to do, what I would like to have in 10 years from now, this is what I would like to have in 10 years from now. So an autonomous machine that can fly very agilely, almost, so agile that actually will almost look like a bird, or even better than a bird. The problem is that in order to have a machine that can be autonomous and agile and lightweight at the same time, it means that you have to solve a lot of challenges, not only in perception, but also control. And by the way, the drones that you see in this video commercial by Lexus were mostly computer generated, while a few ones were controlled by a motion capture system. The company who actually did this video was Camel Robotics, a startup from Vijay Kumar at UPenn, which was 1 year later bought by Qualcomm, and now is behind the Qualcomm Snapdragon Flight board, by the way. So in order to achieve my dream, of course, one of the biggest challenges that you have to address is how do you localize without GPS? So there are two ways to localize without GPS. Either rebuild a GPS indoors, also called a motion capture system, and then you're able to perform agile maneuvers like the ones that Vijay Kumar managed to achieve already in 2011. I was a postdoc here at that time. This was the work of Daniel Mellinger and Nathan Michael, about passing through narrow gaps, so about fast trajectory generation. All the alternative way is to actually use onboard camera and computing, and then rely on visual SLAM, visual inertial algorithms for localization and mapping. So the difference between these two kind of approaches is that the first one basically makes the robot blind because it relies on external eyes and external computing, while the second one really makes the robot able to see the world. But now, in order to achieve my vision, there are certain challenges. I think that the robot vision is still quite far compared to to what we would like to do. So I think personally that perception algorithms are nowadays mature, but they are not robust. Because, for example, think of a motion capture system. You have, in that case, a localization accuracy that is constant throughout the whole workspace. So typically it's 1 cubic millimeter wherever you are. While when you use onboard sensing, typically the accuracy decreases with the distance from the scene, and it also depends on the texture. Okay, so you have to take these two things into account, distance and texture. Another problem is that algorithms and sensors have still big latencies between 50 and 200 milliseconds, which puts a hard bound on the maximum agility of the platform. So you cannot move that fast because you have a high latency. So we need faster sensors and algorithms. And I will show you later that event cameras allow you to basically tear down some of these barriers. Another big challenge is that control and perception have been mostly considered separately by the two robotics and computer vision communities. If you think about SLAM, SLAM has basically, kept all the roboticists busy for 20 years, trying to build visually appealing maps for navigation, but very little work has been done on controlling robots, for example, to improve the quality of SLAM, in order to perform certain tasks. So I would say most of the work has been done for the sake of SLAM. So instead, when you fly a robot, when you move a robot more in general, and the robot is actually vision controlled, so you have to move the robot in a way that, for example, you move over areas that maximize the texture in the scene, because if there is no texture, you cannot localize, okay? So these things actually make a lot of sense for a robot, Another problem is that you know that those very well. So basically, computer vision doesn't work in low texture. Also, when there are problems when you have scenes characterized by a high dynamic range, and also when there is motion blur. In these cases, of course, you can use complementary sensors like an IMU that can actually cope well with the high-speed motion and with HDR scenes, but they are proprioceptive sensors. So there is still an advantage to have sensors that are exteroceptive that can actually cope with HDR and motion blur. And in robotics, HDR is a quite difficult problem. Actually, HDR also caused the death of the driver in the Tesla accident 2 years ago, because there was basically a white truck that suddenly appeared in front of the radar, in front of the mobile eye camera of the car, and basically made the truck totally invisible to the camera because it was basically on a bright sky. Another problem, as I just mentioned, is motion blur, and the only way to tackle motion blur at the moment is using IMU or trying to model the motion blur, like, for example, see the work of Andrew Comport. So I will start now talking about robust vision inertial state estimation, and some of these ideas, actually more opinions, also can be found in these 3 papers. The more recent one is the one with Hossein Eira, John Leonard, and Jan Reed about the future and the past of simultaneous localization and mapping, and towards the robust perception age, which was recently published in Transactions on Robotics last year. So I would say that what you see now is more or less the state of the art in visual odometry, so monocular visual odometry. So this is called keyframe-based visual odometry, and it was pioneered by George here in this room. And basically, this is a very high-level recap of the idea. So if you use a single camera, how do you keep track of its motion and simultaneously build a map of the environment? For example, one idea is to first triangulate points using, for example, the 5-point algorithm, and then localize every further frame with respect to the existing point cloud. And this works well as long as you remain in a small neighborhood of the existing point cloud, but then when you want to actually extend the map, what you want to do is to basically create a new keyframe, triangulate new points, and then continue like before. So, and this is called, therefore, keyframe-based motion estimation, because basically what you do is that you marginalize out frames, you only retain the frames that are important, and these are actually called keyframes, so saving a lot of computation time, especially for relocalization and loop closing. And now, keyframe-based visual odometry is used in all the state-of-the-art visual odometry algorithms. For example, SVO, ORB-SLAM, LSD-SLAM, DSO, to just cite a few ones. But then the main question is how do we do frame-to-frame motion estimation or frame-to-keyframe motion estimation? So there are two different approaches to do that, which you know very well. One is called the feature-based approaches, and the other one is called direct or photometric-based methods. In feature-based approaches that actually have dominated the literature on structure from motion for about 30 years, they consist in extracting features from the previous and the current frame, then computing the motion, the relative motion, by minimizing the reprojection error. The problem with the feature-based approaches is that although they cope very well with large frame-to-frame motion, they can actually be quite slow due to the costly feature extraction and matching, and especially because of RANSAC. While instead, in photometric direct methods, actually, since you're using all the information in the image, basically you can achieve a higher precision and robustness. And actually, very interestingly, if you increase the frame rate of the camera, the algorithm converges faster. So you end up having an algorithm that actually is much faster than feature-based methods. Conversely, in direct photometric methods, because basically they work best if you're already very close to the Base-Minor convergence, they do not cope very well with large frame-to-frame motion. So the frame-to-frame motion has to be very, very limited. So what we proposed in 2014, it was SVO, which stands for Semi-Direct Visual Odometry. And the idea here is to basically take advantage of both feature-based and direct photometric methods. The idea here is to use direct methods for frame-to-frame motion estimation, and to use feature-based methods for frame-to-keyframe bundle adjustment or nonlinear refinement. In this case, we also do not rely on all the pixels in order to make SVO actually very fast. So here, one of the things that we wanted to actually maximize was the speed of the system. So we wanted an algorithm that could actually run faster than real time and had very low latency. So in order to make this algorithm very low latency, what we did is that we only rely on sparse points that can be either randomly selected from the image, like also DSO is nowadays doing, or for example, select them randomly from also edges in the image. So we ended up with SVO being super fast. It only takes 2.5 milliseconds per frame to compute. And these are actually the timings computed on an i7 laptop. And as you can see, SVO is much faster than the state-of-the-art, for example, compared to ORB-SLAM and LSD-SLAM, which actually take 30 milliseconds per frame, after disabling, by the way, the loop closing. Otherwise, they would actually take even longer, like almost 100 milliseconds. And also notice that the SVO is also keeps the CPU load very, very low. It consumes half of basically of a CPU load, while ORB-SLAM takes almost 2 cores, and LSD-SLAM more than 2 cores. So all these timings were actually computed over thousands of trajectories on the UROC datasets. So they were run for many, many, many times, by the way. And they can be found in the TRO paper of SVO. We also recently extended SVO to cope also with different models like fisheye, catadioptric cameras, and also multi-camera systems. So what you see here is SVO working on 4 cameras in real time on a CPU. And in this case, what we do is that we actually track many more points. So here we were tracking 1 pixel every 8 in order to provide very high resolution depth maps. And one thing that actually we have in SVO, which makes the system especially robust for flying robots, especially in dynamic scenes, is the way we do depth estimation. So this is totally probabilistic, and this is not something new, because already the MonoSLAM of Andrew Davison was actually using a probabilistic approach for depth estimation, especially based on a particle filter. But what actually we did differently from MonoSLAM is that we don't use a single variate distribution, but rather a bivariate distribution for the depth. So we use D is basically, for modeling the distribution on depth, and this is actually a heavy tail distribution, because basically we assume that a Gaussian distribution models well the feature matching process. But when you have outliers, these can actually be modeled better with a uniform distribution. And actually, we found a study from Hernandez. So there is a paper by Hernandez that actually analyzes exactly the influence of outliers, and they find out that a heavy tail distribution like this one models well the feature uncertainty as well as the outliers in the system. So we use basically this combination of a Gaussian plus a uniform distribution, also called heavy tail distribution. So we have two parameters that we want to estimate in real time for each feature, by the way, which are ρ. ρ stands for the probability that the point is an outlier, an inlier, and d is basically the distance. So, and we solve this basically actually using moment matching. So we have a closed form solution for estimating these two parameters. So what SVO is doing in background is basically this. So we estimate the depth uncertainty and the inlier ratio for each pixel. In this case, we are only displaying the depth uncertainty, not the inlier ratio. So what does it help for? It helps, for example, to navigate autonomously over dynamic scenes. So here we have a drone that is flying autonomously with a downward-looking camera. So it's looking down, and I asked my master student to volunteer and move below the quadrotor, and actually to wave his hands, to also move his legs, in order to try to disturb the quadrotor as much as possible. But the quadrotor actually remained, quite undisturbed, so it didn't really care about the movements, because actually the depth filters were able to distinguish inliers from outliers, and therefore all the moving points were not considered for mapping as estimation. So the quadrotor here was following a figure 8, and it was not disturbed at all by the movements of the person. And you can see, in fact, that the green points that are mapped are belonging to the static part of the scene.
How sensitive is it to the initial settings of ρ?
So ρ is the inlier ratio.
Yeah.
At the beginning, we assume that the inlier ratio is 100%, but the point is that as you start actually moving away, basically, I have a slide. If you remind me at the end of the talk, I can move to a different slide, and I can show you how the uncertainty evolves over time.
Yeah,
okay? That would be very interesting. Yeah. But we start with 1, okay? And then we let a Bayesian filter to evolve using multiple frames. In the TRO paper of SVO, we also compared SVO against LSD-SLAM, DSO, and ORB-SLAM on different data sets. These are, to my knowledge, the best data sets because they provide the ground truth and all the ground truth, basically, and very well calibrated parameters. So there is the EUROC MAV data set, which conceived for drones. Then there is the Imperial College London synthetic data set, and then there is the one from the Daniel Kremer's lab. So here you can see a few ones. Here I show basically the performance results of the 4 algorithms, SVO, ORB-SLAM, and DSO, and LSD-SLAM on 10 datasets of the EUROC dataset. And here what you can see is that basically they all have a very high accuracy. For example, here you can see over a 60-meter trajectory, we have about 10 centimeters error with SVO here, 60 centimeters with ORB-SLAM, 5 centimeters with the DSO, and 18 centimeters with LSD-SLAM. By the way, we disabled loop closure for LSD-SLAM and ORB-SLAM in order to enable a fair comparison. Here, we were not able to actually initialize DSO because actually the EUROC sequences have increasing complexity, so faster HDR and other things. However, you can see that also LSD SLAM was not able to be initialized well, while DSO actually performed very, very well. And also it gets a higher accuracy than, for example, SVO, which is the second best one here. And the reason is because DSO actually, although it's sparse like SVO, and they use more or less, so they track about the same amount of features, what we didn't have in SVO, which DSO has, is this photometric calibration of the camera, which is exploited in the way they actually they minimize the photometric error. So they basically compensate for the exposure time within the photometric reprojection error. And this is something very, very important to do in order to achieve some slight robustness to high dynamic range scenes. Another thing that we try to investigate in this TRO paper is also comparison between sparse, semi-dense, and dense approaches. So dense can be, for example, algorithms like DTAM or ReMode from a former postdoc, LSD SLAM as a representative of semi-dense approaches, and SVO or DSO as a representative of sparse approaches. First of all, notice that we have a huge difference in the number of pixels that these algorithms are actually tracking. So if you rely on dense approaches, you track on average 300,000 pixels, because that's the effective number of pixels in a VGA image. LSD SLAM tracks on average 10,000 pixels. It depends, of course, on the number of edges in the scene. SVO and DSO track on average around 2,000 pixels. So that actually explains also the computational burden of these algorithms. But what we tried to investigate in this paper was what is best in terms of accuracy. So what we did here is that we used the Blender to generate a huge scenario, which consisted in several kilometers of trajectory in an urban canyon. And what we did is that we wanted to benchmark the convergence rate of dense, semi-dense, and sparse algorithms with respect to the distance between the two frames, with respect to your trying to estimate the relative motion. So distance between the current frame and the previous frame. As you would expect, as you increase the frame distance, so the motion baseline, of course, the convergence rate should actually go down, because these are photometric-based methods, okay? They are not feature-based. So if you get too far, of course, it's difficult to actually let them converge. So what you can notice first is that dense and semi-dense methods perform similarly in terms of convergence rate. And this actually is not surprising, because I would say that the weak gradients are not informative for the optimization. So only high gradients, large gradients actually really contribute to the photometric error minimization. What we found also interesting is that instead the sparse methods perform worse than semi-dense and dense methods when the motion baseline is above 30%. However, notice that when the motion baseline is below 30%, which is already a lot of overlap if you consider, like, a high-speed camera, then in this case you can see that the convergence rate is actually quite similar, at least in this region over here. So the sparse method, we can say, perform equally well for overlaps up to 30%. Okay, so I think this is also quite interesting, because it means that basically when you have a high-speed camera, high frame rate camera, actually there is not much gain that you could get in principle in terms of accuracy in using sparse methods. But of course, there are other advantages in using dense methods, which is, for example, they increase the robustness with the motion blur and the focus. So one of the papers where I read about this was the one of DTAM in Tricia Newcomb's paper, that basically they actually claim that if you use dense methods, you can actually cope better with the motion blur and the focus. And also Andrew Comport has an ICCV 2013 paper where they showed that with dense methods, they cope better with the motion blur. So there are, of course, advantages when you want to achieve a higher robustness. Let's now change completely topic, and now let's talk about visual inertial fusion. So first of all, what is the problem that we are trying to solve when we have a single camera and an IMU? So this is the problem, the equation that we try to solve. So x is the current position, and s is the unknown absolute scale factor. An IMU usually gives you accelerations and angular velocities. here I only show the acceleration, then there would be also other equations for the angular velocity. But there is a bias that is usually due to pressure and temperature that is not known in advance. You can initialize through a calibration procedure the biases, but actually the biases, they vary slowly over time, but they can be modeled like, there is a paper by Stargios Roumeliotis that says that the bias evolves slowly and its derivative can be modeled as a Gaussian process. But anyway, it's an unknown that should be also calibrated and refined estimated over the trajectory. And G is usually known. Of course, it depends on the height. So typically we have three unknowns over here, and one of them is basically the initial velocity, because when you integrate the acceleration, of course, you don't know the initial velocity. However, there is a paper by Agostino Martinelli from IRIA in Grenoble, which is the first and only at the moment closed-form solution for the visual inertial fusion problem. So he found that both the absolute scale, V0, and also the biases, by the way, can be determined in closed form with just one single feature observation and at least 3 consecutive views, provided that you have, of course, acceleration, so non-constant speed. So he found that actually this problem can be solved with a single feature, and the more features you have, the better, of course, it will work. And so you could also have a one-point Ratzan algorithm, which he also proposes. This closed-form solution at the moment is not really being used by anyone. I would say we have used it in my lab, but I would say it's very useful because in principle you could use a closed-form solution to initialize your absolute scale and initial velocity, and then track those entities using, for example, a Kalman filter. So at the moment, typically, these systems work by initializing the absolute scale, either assuming that the phone, for example, is at rest when you start the visual odometry, or by using a loosely coupled approach where basically first you double integrate the acceleration, then you feed this through to the filter, which is actually not very good. So this would actually work better. So we actually have a paper at RAL 16 where we showed that this increases the accuracy for tracking methods. But then once you have initialized anyway both the absolute scale and the V0, how do you track those entities? So here there are 3 different approaches. There are filter-based approaches that typically only update the last state, the last pose. The problem is that, as you know, Kalman filters have the problem that the covariance increases quadratically with the number of features. So what you want to do in filter-based approaches is to keep the number of features low. So typically they only track around 20 features. So if you think about Google Tango, they also actually track a very few number of features, around 50. And there is an algorithm that is actually now used in Google Tango and also the Apple ARKit, which is the MSCKF, multi-state covariant multi-state constraint Kalman filter by Mouriges and Roumeliotis. But then there are other 2 approaches that, conversely from filter-based approaches, what they do is that they update not just the last frame, but they update the last n frames. So they work in a sliding window estimation approach. Or alternatively, they estimate, so they update the full trajectory of the camera, including all the frames and the AIMU. The problem with these 2 approaches, so sliding window, full trajectory estimation approaches, is that they are more accurate, of course, because they use more information, but of course they sacrifice a little bit the efficiency because they actually need to optimize over a larger number of parameters. And these are actually the main algorithms that are being used in this kind of approaches. How do they work? So how do optimization-based approaches work? So optimization-based approaches work trying to solve basically a post-graph SLAM problem, where basically here in this case the gray triangles represent the frames, for example, I don't know, 50 Hertz, and then the red dots are the IMU measurements that, for example, come at 200 Hertz or 1 kilohertz. And then here in this case we have, for example, just a single 3D landmark, but in general you have many, of course. So what this optimization-based approaches try to do is to compute, the minimum energy configuration of this graph, such that basically 2 error terms are minimized simultaneously. On one side, you want to minimize the prediction error between the prediction by the MU and the position estimated by the visual odometry, which is actually known up to an unknown scale factor. And then on the other side, you want to also minimize the bundle adjustment term, so the reprojection error. Of course, these 2 terms will be weighted by some coefficients that will need to be tuned. The problem with this post-graph optimization approaches to solve the visual inertial fusion problem is that typically these graphs are very dense in terms of number of parameters and number of frames. So what we proposed in this paper with the Freund-Dellert, RSS 2015, is to first sparsify the graph by skipping frames and by pre-integrating the IMU between only keyframes. So we basically represent multiple IMU measurements into a single post constraint in order to make the system actually more manageable from a computational point of view. And then we use ISUM to solve this graph. And ISUM stands for incremental smoothing and mapping, which is a nice algorithm similar to Google Ceres or G2O. But what it does nicely is that it only updates the poses that are affected by a new measurement. So this makes the algorithm extremely efficient for post-graph optimization problems. In fact, it can run in real time even on a smartphone processor, actually at 50 Hz. So we managed to run it on an Odroid computer at 50 Hz.
Have you managed to characterize the sparsity versus accuracy curve? Like, how does that look?
So in terms of accuracy, this is what we did. Later we can talk about more about this. So we also use the EUROC MAB dataset, which is the only public dataset that provides synchronized IMU and camera frames plus a motion capture ground truth. Here we compare against Google Tango, which uses a filter-based approach, specifically the MSCKF by Roumeliotis, and then OCVIS, which is a sliding window estimator. So it only updates the last n keyframes. So here we show the translational error versus the distance traveled. So as we expect, the drift increases, of course, but as you can see, our full trajectory estimation performs better than MSCKF and then OCVIS, and this is because actually we are using more information, okay? Now I want to show you some videos of how we used this visual inertial state estimation on our drones. So this is one of our drones, and the main sensor is basically a global shutter camera, which has a little a resolution that is slightly higher than a VGA camera. It also has a high dynamic range and outputs frames up to 90 frames per second. It also has a PX4 autopilot, which we use for reading the IMU as well as controlling the motors. And then the main computation happens on an Odroid XU4, which is basically a quad-core computer with 2 GHz. And there we have a Linux, Ubuntu, ROS, and we run all the SVO and visual inertial state estimation as well as control and path planning. So all running on board. Using this system, so this is a system that we have been using for over the past 5 years. We have done several works. So here you can see, for example, the performance of the system under disturbances like pulling and pushing the quadrotor. Here you can see the system following a figure 8. Here we achieve about 2 centimeter accuracy, and the higher you fly, the more the accuracy, the uncertainty will increase, of course. Here you can see how the system reacts, for example, to larger disturbances, like when you toss the quadrotor in the air. And this is actually only using, again, a single camera based on SVO and no GPS. And this is to show that basically there is the need to use a low latency state estimation algorithm, because if the latency was too large, then it would actually it wouldn't be able to reinitialize the map and therefore stabilize. So you need something that is below 10 milliseconds. Now we are using since a few months ago, we switched to a different system, which is now based on the Qualcomm Snapdragon Flight board, which has the nice property that it integrates a forward-looking camera, a downward-looking camera, plus a Qualcomm quad-core processor on the same board. And it weighs less than 50 grams, and this is great. So the whole quadrotor, including the Qualcomm board, weighs 200 grams, and is even safer than the previous one. In addition, it has a forward-looking 4K camera that can be used for other tasks. We also use a carbon fiber frame to make it extremely lightweight. And here you can see the system all relying on onboard visual inertial state estimation. So it's even more agile than the previous one, because actually the agility is inversely proportional to the size. Okay? The agility is usually measured in terms of angular accelerations. Now, so far I was talking about visual inertial fusion, assuming that the camera parameters are left unchanged. But, one of the parameters that you could, in principle, tune could be, for example, the exposure time. And that's what we try to do in this ICRA paper this year. So typically, one of the biggest problems in visual inertial estimation is how do you cope with the scenes characterized by high dynamic range. This is, for an example of high dynamic range. You see basically the high dynamic range here is dramatically changes among these different scenes. And the problem is that when you have an overexposed or underexposed scene, typically you will lose track of the features unless you fastly compensate for the illumination change. But then if you even compensate, sometimes you change the appearance of the patches and then you lose track anyway. So the problem is because the built-in camera out exposure is usually optimized for image quality, so for photography, and not for visual odometry. So the idea here was to actively adjust exposure time in order to maximize the robustness of visual odometry. So the control approach is the following one. So here is the visual inertial, so this is visual odometry or visual SLAM, which is not changed at all. What we change is basically the exposure time of the image before feeding it through the visual odometry. So we have the camera returns the image. This is fed to our active camera control strategy that basically modifies the image, so enhance the image exposure time, so illumination, and then it's compensated through an affine transformation, and then it's fed to the front end of the visual odometry. What is our control strategy? The control strategy is the following one. Basically, we assume that we have already photometrically calibrated the camera, so we know the radians for each exposure time. And therefore, the next exposure time is going to be equal to the previous exposure time plus a certain manually tuned gamma times this ratio over here, where this ratio is basically a function of the partial derivative of a percentile of the gradients. So in principle, what you want to do is maximize the number of features in your VO pipeline. And the number of features depends on the number of gradients. So there was a paper by David Shim, KAIST, South Korea, in IROS 2015, that they tried to maximize the sum of squared gradients in the image in order to adjust exposure time. But actually, we found that this is not very robust to different scenes, and it's actually better to maximize a percentile, like, for example, the median of the distributions. By doing this, you achieve a much higher robustness of the system in HDR scenes. And here you can see an example. So we apply this system to all the state-of-the-art algorithms, so like Orup SLAM, DSO, and SVO, and we show that all of them actually get enhanced. For example, in this scene, we are moving the camera in front of a road sign that is occluding the sun. And as you can see, this is the raw implementation of Orup SLAM, where the image suddenly gets overexposed or underexposed, and so it loses track of features, while in the upgraded version that uses our exposure control and compensation, actually the features are not lost, okay? Because this is taken into account by changing actively the exposure time. This is another example. In this example, actually, we are showing Orup SLAM. Here we have another HDR sequence where here we have a very bright light source, and as you can see in the raw implementation, the features are lost, while after compensating for the exposure time, the features can continually tracked. Okay? So this actually very simple approach provided to provide a little bit of robustness and increase robustness over HDR sequences. But of course, it will not scale to all possible HDR sequences. For those, we will see in a little bit, it's actually better to even use event cameras. Yes?
The control response, is it for every frame?
Yes.
Okay.
Yes, and there is a delay of 1 frame.
Okay.
So we actually control the camera driver. We are using an Aptina sensor here, a matrix vision camera. So there is a delay of 1 frame.
Any information carried from the past?
You could, but we don't. But you could indeed. Now actually we have a paper on arXiv where basically we also add some deep learning. And we show that you even get a higher robustness. Yeah. Yes.
So what's your thoughts on these cameras which are now coming? They've been coming for a while now, but they're becoming cheaper, which use multi-slope to really increase and where the slope points can be programmatically changed on the fly. Just in your experience, have you found that they're worth it or?
We haven't used them, but why not? Absolutely. Yeah, yeah. At the moment, actually, I have most of my people now working on event cameras.
I see.
For reasons I'll tell you later. But of course, that makes sense also what you are proposing. So now, yes.
Maximizing the gradient information
Yes.
equally apply for both photometric and
Exactly.
feature-based.
Yes, correct.
And this doesn't affect the DSO part where DSO actually does control for the exposure.
Yeah, no, DSO doesn't control the exposure time.
But
No, it only adjusts. So in the they apply in a fine transformation of the intensity of the image, which depends on the delta t. But delta t is constant. It depends on the camera frame rate. On the camera, it's not changed. We changed that, and then we use the same affine compensation as DSO, but which is actually standard. Okay. Okay, now I'm going to switch topic, and I'm going to talk about event cameras, and especially for low latency state estimation. Again, drone motivation behind, since I love drones and robots, and my goal is to one day fly as agile or even faster than birds, so I found this beautiful video from National Geographic that shows a sparrowhawk that in 4 seconds, so this is real time, it slaloms among trees, it passes through a narrow gap, and poof, it makes a bird disappear suddenly. I like this video because it shows that basically, you know, what you could in principle do with a bio-inspired eye. So with a camera that has the latency of low temporal discretization of the human eye. In fact, the problem is that, you know, if you want to go faster, we need faster sensor. Why? Because the agility of a robot is limited by the latency and temporal discretization of its sensing pipeline. I try to explain it in different terms. Basically, a quadrotor, for example, the motors of a quadrotor have a constant time of about 30 milliseconds. Usually, a constant time is computed as the time it takes that speed to go from 0 up to 80% or 70% of the desired speed. So 30 milliseconds. But if you want to change actually the speed incrementally, well, the latency is below 1 millisecond. And also, interestingly, if you scale down the size of your robot, also the latency will actually reduce. So even to go from 0 to n meters per second, you would actually need less than 10 milliseconds. Okay, and with a small drone like this, or like you know the RoboBee project by Robert Wood at Harvard, well, they have latency of the flaps, which is below 1 millisecond. So there is a very strong interest in developing visual inertial navigation systems with very low latencies. Now the problem is that we are limited by the current technological drawbacks of standard cameras. So in a standard camera, you have frames at constant time intervals, right? Usually every 30 or 10 milliseconds. So every time you grab a frame, then you need to wait a certain processing time to process the last frame, and then you need to wait another delta t in order for the next frame to arrive. So typically, the average robot vision algorithms have latencies between 50 to 200 milliseconds. As I told you, SVO is 2.5 milliseconds, but this is the average robot vision algorithm. Event cameras actually would allow to do low latency sensory motor control with latencies that are much below 1 millisecond, including the temporal discretization. Why is that possible? Because the output on an event camera, as I will tell you in a little bit, is not a frame, but rather events that correspond to pixel level brightness changes in the scene. So this camera has smart pixels. Each pixel, whenever it detects a change of a relative change of intensity, it triggers an event. And an event, you will see in a little bit, is basically a binary signal where basically is the sign of the derivative of the change. This camera is called the dynamic vision sensor, and is bio-inspired. Why? Because it's inspired by the way the human eye works. So in the human eyes, you know, we have per eye 130 million photoreceptors, which consist of about 120 million rods and 7 million cones, which you can find here. But we only have 2 million axons. So the axons are the wires that connect the pixels, our pixels, to the brain. So how is it possible that we have many more pixels than the effective number of wires? This is possible because our eyes fire the information asynchronously. So every time that a few photons hit a photoreceptor, that photoreceptor actually will pass through a receptive field and then eventually will actually fire information asynchronously and independently of all the other photoreceptors. So inspired by this principle, but not mimicking this principle, by the way, Professor Toby Delbruck from my department in 2008 developed the first commercial dynamic vision sensor. This is the key paper. Dynamic vision sensor, or DVS, also called event camera. Okay. The camera can be seen here. So it looks, from the aesthetical point of view, like a normal camera. So there is no way to distinguish an event camera from a standard camera. Actually, they can be now found also in the size of smartphone cameras. Okay, like 5 by 5 millimeters. They can only be bought for now by Inilabs, but Samsung just announced that they are going to mass produce the sensor. So Mark Polyface, for example, bought 2 from Samsung, the Samsung DVS. Okay. A DVS has 4 key properties, which I find very, very interesting, not just for robotics, but also especially for VR, AR, which are the low latency, so 1 microsecond latency of the events, also very high dynamic range, so 140 dBs instead of 60 dBs of standard good cameras. That means that you don't need a black filter if you point an event camera towards the sunlight. This picture was shot in 2015 during the European solar eclipse. And here you can see the moon shape and the fingers of a hand without using a black filter, both at the same time. Okay, so this is to show basically the potential of this camera in terms of high dynamic range. It has a very high update rate, 1 megahertz, and it consumes very low power, which is almost 100th of a standard camera. So 20 milliwatts instead of 1.5 watt of a standard camera. That means that you could also enable like video surveillance applications. So you would only need to change the batteries every once in a while. And actually, the low power characteristic is being exploited by DARPA and IBM in the True North processor. This was a 70 milliwatt neuromorphic computer used in the Synapse DARPA project. So it was a 1 million neural network that was using input from a DVS, and then they showed applications to recognize a few gestures with very low power. But now there is an even better neuromorphic computer that consumes 1 milliwatt. So it's asynchronous in the way they process the information. So they can only process event sensors like a DVSs or also audio DVSs. So there are also. So there is a lot of research also in terms of neuromorphic computing that could be applied to event cameras. What are the disadvantages of event cameras? Well, because the output is asynchronous and there is no intensity information, but just binary information, because these events correspond to pixel level brightness changes, the disadvantages are that basically you cannot apply any of the standard computer vision algorithms that have been developed for the past 50 years of research for standard cameras. Before I go on, let me illustrate better how the camera works. So because the camera responds to relative changes of illumination, basically you can see this camera as a motion-activated edge detector. So imagine that there is something moving in the scene. In this case, we have a rotating disc with a black dot. A standard camera would output frames at constant time intervals. Instead, a DVS would output a spiral of event, which corresponds to what is changing in the scene over time. So here we have X and Y and time. So it's a 3-dimensional, so it's a spatial temporal signal, okay? And as expected, if nothing moves, no events are generated. So you have a drastic reduction in bandwidth. But another cool feature is that there is no motion blur, because this camera works in differential mode, so it does not accumulate photons. Okay? Only the sign of the derivative. Okay? So no matter how fast you throw the camera or you use it, there is no motion blur. Another way to visualize the output of a DVS is to accumulate the events that occurred in the last delta t milliseconds. So we call these virtual event frames. So it's an alternative way to visualize this information, where blue stands for positive changes of illumination and red stands for negative. And notice that points that are farther in the scene fire less events than points in the foreground, and this is quite expected, right? Because it's similar to the optical flow. And there is background noise. which at the moment we model as a Gaussian process on the threshold that actually triggered the events. But we can talk a lot about this noise, because actually there are many non-idealities of the sensor and a lot of work needs still to be done. Let's dig down even more. The pixels of a DVS are even slightly bigger than those of a standard camera. Actually, in the original DVS, there were 40 microns. And you know, the standard pixels are about 6 microns. However, now Samsung managed to scale them down to 9 microns, which is much better. The reason why they are slightly larger still than standard camera pixels is because of the electronics behind each pixel. So you have the photodiode, the photoreceptor, then you have a capacitor. So this is basically the circuitry behind each pixel. So after the photoreceptor, you have a capacitor to basically remove the DC component. Then you have a reset, which basically resets the time at which you want to compute the event. Then you have an amplifier, and then you have two sets of comparators that check whether the relative brightness change is below or above a certain threshold. Actually, I call it relative brightness change, but in practice is the logarithm of the intensity, okay? So let's assume that this is the logarithm of the intensity over time. So whenever the delta of intensity from the previous spike is above a certain user-defined threshold, C, which you can tune, but at the moment it doesn't go below 13%, then you have a non-event. If it's less than the opposite, so minus 13%, then you have an off event, and so on and so forth. And the delta T between consecutive events, of course, depends on when the illumination, crosses this threshold. So it's what is called level cross-level sampling, basically. What you can see from this plot is that if you accumulate the number of on and off events over time, you could reconstruct the intensity of the signal. So people have done it. Actually, the first work was by the people of Toby Delbruck in 2011, and then more recently in 2015 by the group of Andrew Davison, so to reconstruct the intensity of the image, the relative intensity of the image. Okay? And this is actually very useful because you could generate HDR images. So now there are many automotive companies that are looking at DVSs because of the potential for HDR imaging. So a few years ago, one of the first things we did was to collect a data set. Because I'm interested in drone applications, I wanted to see, first of all, how much information is triggered by an event camera during aggressive maneuvers. So we took a quadrotor, we mounted the DVS and the standard camera, and then we flipped the quadrotor, and we use a motion tracking system in this case to control it. So it was not closed loop at the moment. Here you can see the output of a DVS, and here the output of a standard camera, which obviously is affected by motion blur. And here you can see the changing accumulation time for rendering these virtual frames. The first thing you will notice is that these virtual frames are always very sharp. Okay? So one of the first questions that we tried to ask was how many events are important for example, motion estimation? How many? Because the problem is that if you have too large accumulation times, actually then you have motion blur, right? And as you decrease the accumulation time or the rendering time, then of course less and less events will appear. So one could think I could actually accumulate a right number of events and then apply standard line-based or feature-based algorithms here. But this is not what we wanted to do. Because if you accumulate events, well, why don't you then use a standard camera? Because you are increasing the latency. Instead, what we are interested in is event-based vision. That means processing at the resolution of the single events, ideally. In practice, a single event doesn't provide information, but 3 events actually is the minimum amount of information that can be used, okay, for certain problems. So what we are interested to do is event-by-event processing. So try to update the state of the system as a single event is generated. The problem is you first have to model the sensor. So with my colleague Andrea Censi from MIT, we try to come up with a probabilistic measurement model of a DVS, which turns out to be this. What we are saying is that the probability that an event is generated is proportional to the scalar product between the gradient of the patch that you don't know times the apparent motion on the image plane, which you don't know. I'll try to convince you that this model makes sense intuitively. So First of all, the optics on event camera is the same one as that of standard cameras, of course. So you have a standard pinhole camera model. Let's assume that the DVS is just looking at a single patch represented by a black and white transition. So you would agree with me that if you move the DVS parallel to the edge, no events will be generated, while if you move it in any other direction, there will be generation, with maximum generation, with directions that are perpendicular to the gradient. So that's where this comes from. Now we have actually modified this slightly, but at the moment I use this one because it's easier to convey the message. The problem is that now you need these two entities, and you can estimate these two entities, for example, using Bayesian filters. So one of the first works that we did, which took 2 years to review for PAMI, so it came out very recently, is basically using a Bayesian filter to estimate the gradient or the motion alternatively, okay? But now we are getting away from that. Anyway, I'm going to show you some of the results, then later, if you're interested, I can dig down. So here is one of our first event-based visual odometer SLAM pipelines. There is no loop closing, okay? And no relocalization, so it's actually more odometry. You can see that this is the input, so events, and the output is a semi-dense map of the environment, plus the trajectory, estimated in real time. Because the input is basically already semi-dense, is by definition, because it's computed on hardware, the output can only be semi-dense, okay? And notice that the map is pretty reasonable. It looks very reasonable, of course, with accuracy that can be tuned depending on the certain parameters. Here we show you a comparison with a state-of-the-art algorithm running on a standard camera. So here we have SVO running on a standard camera and our event-based visual odometry running on the DVS, event by event. The details can be found in the PAMI paper that just got accepted. So here what I would like to point out is that when the camera starts moving fast, SVO loses tracking because of the motion blur. We don't compensate for motion blur. And it would be very difficult to compensate for motion blur because you will need to estimate the depth. That's what Andrew Comport did in his ICCV paper. While instead the event-based visual odometry continues to track the camera because the events are actually still meaningful. Okay? There is a lot of information spiked. Another thing I wanted to show you is the robustness of an event camera in HDR scenes. So this is my iPhone camera. Notice that the road sign features disappear when the sun shines. And this is what the event camera looks like. You can see that when the sun shines, you can still observe texture on the road sign. And here we show the output, so the estimation of the tracking and mapping estimation. In addition, we also show that you can compute in real time the intensity of the image, although our current algorithm does not need to compute the intensity, because as I told you, we are now moving away from this alternative estimation of image in gradient and of parent motion. We are using an approach which we call contrast maximization, which I'll explain it in the next few slides. Okay, so this is basically to convince you that event cameras have a very high potential for HDR and high-speed motions, okay? But now, what about computing time? So, an event camera, so this is a question typically people ask me, what happens if every pixel spikes information? Well, in that case, there is a maximum number of events that the camera can handle. The current DVS can only handle up to 50 million events a second, but the new Samsung DVS can handle up to 300 million events a second. So using a VGA camera is like if every pixel was spiking at the same time. So that could be done. The point is that then you have to process this information. So if you process it event by event, you would actually need a GPU because you have more information than a standard camera. And then if you use a GPU, then the low power considerations actually, they're a little bit, unusable. So what we try to do is try to rethink also what information is useful. And so we try to see if we could extract salient key points from an event stream. And that's what you see in this video. This is a BMVC paper this year, where basically what we do is that we extract fast-like corners from an event stream. So this is the raw event stream. And then now in a little bit, you will see the corners that are being tracked. So you're familiar with the fast corner detector? Just to recap, typically in the fast corner detector, you say that the pixel is a corner if in a circle of 16 pixels, there are at least 9 adjacent pixels that are or darker or brighter than the center pixel. So here we take a similar thing into account, and we say that since there is no brightness information, we take the time into account. So we say if there are at least 3 to 6 contiguous pixels that are newer than all the pixels on the same ring, and for example 4 to 6 that are contiguous pixels on a smaller circle, then actually this point should be considered as a corner. So we managed to extract these corners with the same complexity as the fast corner detector, same computational complexity, but because the event cameras triggers information much faster, you end up with having a fast corner detector that is 100 times faster than a fast corner detector. Now, how do we do the tracking? So this is now the way that we are changing completely the way we are now doing tracking. We call this contrast maximization. And we are now writing a CVPR paper about it, although some results can be found in this paper, which was accepted, by the way. So if this is the spatial temporal representation of the last, I don't know, delta t milliseconds of the event stream, what we try to do is to compute the motion that over a small time interval will maximize the contrast of the scene. So if you could visualize this as a spatial temporal signal, try to unwarp it temporally in a way that best you can see very high contrast images. And this is something that you cannot do with a standard camera unless you know the depth and you know the convolution filter. Okay? So in a standard camera, basically, when you motion blur the image, you lose the time information. In an event camera, the time information is there. And this, I think, is very, very cool. Now, you can solve this contrast maximization either in a local way per features or globally. Sometimes also globally works, because in the end, the amount of motion is so small that you can assume that the scene is almost planar. Okay? So we try to do both. And they can be run very, very fast, actually. So now I'm going to show you some results. This is a BMVC paper from this year, and also a EU patent. Here what we do is now a feature-based VO plus IMU, so visual inertial odometry with features extracted from the event stream. And to show the potential of this, what we did is that we attached a DVS to a leash and then we spin it in the air. So here is the camera attached to a string, and now we spin it. In the paper we also compare to the raw integration of the IMU, and we show that the drift is, of course, much lower when you integrate the event camera, obviously. Also, we compare with a standard camera. So this is the Aptina sensor without exposure. You can see that when you spin so fast, the images are motion blurred or under and overexposed, so you can't extract features. This is what virtual frames will look like on an event image, and these are the features. We extract these fast corner-like features, and here you also see the performance on an HDR sequence. This is all in real time, by the way. So we use green to represent persistent features, so like in SVO, so seeds that converge, and the blue features are the ones that are only initialized but cannot be tracked. And now what we did, so we have an ICRA submission, is that we apply this to a quadrotor and we fly with it only. So this is the first autonomous flight in closed loop with an event camera. So here we are using our proposed VIO, feature-based, event-based. Okay? And to show the potential of this, what we do now is that we are going to switch off the light. And the quadrotor continues to fly without being bothered. We tried that with the recent DJI drones and Qualcomm drones that have their own VIO. Oof, they crash immediately. Okay. We also tried with SVO, of course, because the problem is that, first of all, you have an abrupt change of illumination when you switch off the light, on and off, and also because of the low light. So all the standard cameras in low light would suffer from strong motion blur. Actually, you're going to see this here. So this is what is going to happen now. So These are event frames, virtual event frames. These are the events only. These are standard frames. The standard frames basically do not track features, while the event frames continuously track features, both in light and in low light. Of course, there has to be a little bit of light, otherwise the event camera doesn't see anything, okay? But because of the high dynamic range, they can actually deal with the full moon light according to the datasheet, full moon. This is another experiment where the room was partially illuminated and partially with low illumination. And here you're going to see that when the quadrotor flies in darker areas, let's see, the frames get motion blurred or too low light, and therefore you can't track features anymore. And by the way, in this pipeline, in this paper, what we did is that we combine frames, events, and IMU, tightly coupled, all together. So, and the paper is already on archive if you're interested.
With these cameras, do you have the ability to set the threshold when the event is
Yes,
occurring?
but not explicitly. That means there is not a parameter called C that allows you to set the threshold explicitly, but you have 12 parameters whose combination will set the threshold.
And when that event is triggered, that like basically does a reset on that little circuit.
Yes.
essentially.
So basically you have the reset time. It's one of the 12 parameters that you can set. But for this positive and negative threshold, there is not an explicit parameter. So only the combination of several other parameters will give you the effective
So if I
threshold.
move the camera very slowly, it will eventually trigger an event.
Yes, you will always trigger events. But depending on the reset time and the other parameters, you can actually trigger the sensitivity in a way that you see more or less events. Okay? If you see less events, you will notice only background noise, by the way. By increasing the sensitivity, of course, you decrease the SNR, so you have more noise. Okay, but we usually also have filters for that, like, we check whether the pixel is isolated in time and space, and then we can actually remove it from the event stream. So in conclusion, the message of this talk is the following. I think Agile Flight is very far in time, probably 10 years from now. Perception and control should be considered jointly. For example, think of this active exposure time control and compensation. So there is a strong advantage in using active perception approaches. What about perception? So visual inertial state estimation, or SLAM, I think the theory is very well established. In fact, now there are many less theoretical papers in terms of that try to tackle, the increase the accuracy, but more papers that try to tackle the robustness of the systems in terms of different parameters. For example, with high dynamic range scenes, high speed motion, low texture, and dynamic environments especially. Here, I didn't talk about dynamic environments. We also try to model outliers with these high heavy tail Gaussian distributions. I think there is also a big potential for machine learning. Actually, now we are also using deep learning on the event cameras to try to see if we can provide the contextual information to improve even robustness in certain scenes. In general, I think event cameras are revolutionary because they provide robustness to high-speed motion and high dynamic range scenes, and they also allow low latency control. And this is actually some ongoing work. And also, I think they are intellectually challenging because in the end, standard cameras have been used for over 50 years. So there is a need of a change. In this slide, I try to summarize the state of the art of the past 50 years of VIO research. And this is my honest opinion. You may disagree. But basically, I think that from 1980, when Hans Moravec published his key paper on stereo visual odometry for the Mars exploration rovers, until 2000, the research was dominated by feature-based approaches that increased a lot in accuracy. So we went from 5% to 1% of the travel distance in terms of drift. What happened from 2000 onwards? Well, then GPUs came, and so also direct photometric methods came. And direct methods actually did not increase too much in accuracy, maybe slightly, fractions of percent, but they actually moved us on this other line in terms of efficiency, because direct methods are more efficient than feature-based methods. And if you use them in combination, you actually have even higher efficiency. And they also increase in terms of robustness, especially against the motion blur and the focus. Now, when you use an IMU, in addition to a camera, you can provide an up to 10 times better accuracy. So because an IMU basically brings the error down to 0.1% of the travel distance. So 1 meter every kilometer of trajectory. Okay? And then if you use an event camera, you can actually improve on all three axes: accuracy, efficiency, and robustness. And probably using other cameras like this one. Now there is also another camera, like smart cameras, like the SCAMP from the University of Manchester, which I also want to work with, that open new scenarios. So I think there is a lot of interesting research to do and going on, which is difficult to track. So since these event cameras can only be bought by this company at the moment, we published a data set called Event Camera Dataset and also a Blender simulator, where we include IMU frames, events, and ground truth from a motion capture system. So we have 30 different sequences, both indoors, outdoors, HDR, high speed, and low speed. And very recently, we also published this list of all the papers, code, videos, companies on event-based cameras. Now there are 5 companies producing event cameras, but only one from which you can, at the moment, buy. So here you will find over 200 papers organized by category, and you can contribute to the list. It's on GitHub. So, and with this, I thank you for your attention. Sorry if it took me longer than I expected.
I was just going to say, definitely sold me on improving performance and robustness using event-based, but maybe I missed the opportunities, but I'm curious what you think you can do with an event-based camera that improves accuracy of tracking. Or do you feel like you...
Yeah. Sorry, I can comment on that. So an event camera outputs almost 10,000 more information than a standard camera, if you say that a standard camera works at 100 Hz. Okay? So you have a higher temporal resolution, up to 1 MHz. So a higher temporal resolution means more information. By information theory, therefore, more precision. What we did here in this paper from PAMI, we were using at that time, 2 years ago, one of the first generation of DVSs that has a 128 by 128 pixels. And here we plot the error, XYZ, roll pitch, XYZ. And we compare that against SVO that is running on a higher than VGA resolution image. And notice that here we get the same comparable error, although we are using a 20 times smaller resolution image. This is because of the higher temporal resolution. Yeah. Now, the question is, what is the best way to fuse information from an event camera with that of a standard camera? So there are different ways. In the last ICRA paper, what we were doing is that we were now extracting features from both cameras and then feeding them to a filter. But actually, we have also a paper that is at the moment only fundamental, which we didn't yet make work in real time, is that we try to also tightly couple basically the standard camera with the event camera, and basically try to modify that probability, the probabilistic measurement model to also consider the gradient that you have from the standard camera. So let me go back to that slide. You see here, I told you an event camera doesn't give you the gradient, but the standard camera does give you the gradient, but passed in time. Now you can basically, feed forward that, okay? You can use an IMU, or even the events track features, and then basically in a sliding window estimation way, try to fuse this information. So you can find the idea in this paper, how to do that. But that was at the moment all in 2D, and now we're trying to extend this to 3D, the 6th.
Question about your active exposure control scheme. Does that, because you're trying to increase the gradient of the image aggregate, does that also help you with motion blur, or is it only in situations of dynamic range?
No, we don't compensate for the motion blur there. Indeed, explicitly.
Right.
Okay. So no, that would
be a side effect of the system.
That would be a side effect of the system. Of our system. Yes, because of course in low light scenes you would try actually to increase the exposure time. Yes, that would be a side effect. Mm-hmm. Yes.
How do you calibrate the event cameras?
Good question. So I haven't told you the whole story. There is a new event camera which is called the Davis, Dynamic and Active Pixel Vision Sensor, that outputs events and frames and IMU. And the events and frames are coming from the same pixel array. So if you calibrate the frame part, you are automatically calibrating the event camera. Until this Davis became commercially available, we were basically moving the camera in front of a checkerboard or of a flickering checkerboard pattern on a screen. That's how we were doing that. Or blinking LEDs. Samsung uses blinking LEDs.
You mentioned that the computer vision algorithms need to change for event-based.
Yes.
But what about the control aspects? Do you think the control algorithms that we're using computer vision, they need to have a different paradigm shift as well for event-based cameras?
Which control algorithms?
I mean, any kind of PID loop, any kind of L1 adaptive control or anything like that.
Yeah, absolutely. This you have to reframe all these control algorithms in an event-based fashion if you want to do it event-based. There is a group led by Riyad Benosman at the University of Paris where basically they even implemented an event-based Hauff transform, a Fourier transform, for example.
Okay.
Yes. No, there is also plenty of contributions there.
Okay.
Absolutely.
Is it on the web page?
Yes, you will find that there too. Indeed. Yeah. By the way, there is this slide. This is a new Samsung, generation 3 already, by the way, DVS, compared to the original DVS and the Davis sensor. So, the Davis, which came out in 2008, had the 128 by 128 pixels, larger surface per pixel, 40 microns, and only 1 million events per second at the most. The Davis, so frames, IMU, and events, has almost a higher quarter VGA resolution, smaller pixels, but still high, up to 50 million events per second, higher sensitivity, and lower noise. Now the Samsung Generation 3, which we have 2 units in my lab, has a VGA resolution, much smaller pixels, lower sensitivity in low light, so the original Davis has better sensitivity, 0.1 lumens, but they can up to 300 million events per second, so all pixels spiking, less than 13% sensitivity, and lower noise, so higher SNR. But it only has events and IMU, no frames for now.
What is the IMU really getting you in this case now?
Well, because if you want to go for so if you want to go for AR VR applications, I mean, in the end, also robotics in general, all you may still have problems, right? So why not using an IMU when you
Is
have
the
it
IMU
there?
still running faster at this point?
No, it runs slower because typically IMU go up to 1 kilo. Low cost IMU go up to 1 kilohertz. Okay.
I guess the question is how many events does one need to make a
Typically, we found,
complete observation?
yeah, in our application, that would basically mean like a 10,000 FPS camera.
I see.
So 10 times faster than an IMU. But what are the applications that really need such high speed, right? That could be a question. For drones, that would make sense for low latency sensory motor control. For VR AR, I would say that for low power, you may want to maybe trigger the camera at a lower frame rate and use the event camera for updating your pose in the blind time between frames.
Because
For
somewhere
example.
the IMU is going to be observing gravity.
True. Yeah.
That's all it's really going to be doing.
Yeah, exactly. Yeah, motion prior, indeed. Yeah.
Well, for getting some sort of like
Awesome.
baseline
Yeah.
rotation.
Well, when there is no illumination, of course, the IMU then provides information. Of course. Yeah. Yeah. There.
I was wondering if anybody tried object detection or recognition. using
Yeah, you will find that in the list. Yeah, the people in Paris have done that. There is a company called Chronocam that raised already 30 million from Bosch and Intel that has shown. So we organized the first workshop on event cameras at ICRA this year. Chronogram was there, Samsung too, and Chronogram showed basically some results on detection of pedestrians and cars for automotive applications using only events, so with very low latency. Although the success rate was in the order of 70%, which is 20 times less than what you get with standard cameras at the moment. But I think also they were not using sophisticated, deep learning algorithms, very simple things. Also. Yeah.
So I have a question from the audience from Drew Steedley. He asks what happens under fluorescent lights?
In?
Fluorescent lights.
It's a very good question. So one of the thresholds that you can tune is the cutoff frequencies of the camera, minimum and maximum. You can tune it in a way that is above the cutoff frequency, the frequency of the fluorescent light, which is around 50 or 60 hertz. So if you put it above, then you don't see anything, okay? But already the minimum is around 50 hertz. That means that, the event camera doesn't see, it's too slow, basically. The flickering is too slow for the event cameras to see. But you can tune it. So with some fluorescent lights, it depends on the duty cycle. But it's, if it goes down very quickly, so then you have a very abrupt changes. Then in that case, you would actually be able to see it. So it really depends on the type of fluorescent light. But in general, you can tune it in a way that you don't see it.
I guess the LEDs, which might sort of flicker.
Yes, some LEDs actually give problems. So in that case, you would always see information. You would see actually blue-red all the time. Yes.
Can you tune it so you only see fluorescent light?
Say again?
Can you tune it so you only see fluorescent light?
Only see fluorescent light,
Or light of a given
but then you see everything.
population?
The problem is that then you see everything. And all the pixels will spike. That means that basically it's, it's not usable anymore. That's the problem.
Yep.
When you switch off or on a light in that quadrotor experiment, all the pixels spike in a few microseconds. Actually, you can see the light going down. And we basically observe a glitch in the number of events, and we just filter it. Okay, so we skip all those events. Mm-hmm.
Does the camera typically generate events in pairs, like for example?
Yes, of course.
Typically, you see the negative and
Yeah, very few. So what happened? Because basically the triggering time is continuous in time. It's analog, but the reading is digital. And it happens at 1 megahertz. Of course, you could trigger it faster, but that's the way that it's done at the moment. That means that basically in that, if there was a larger brightness change, you would actually see more events. Typically 2 or 3, but you don't see them very often. I would say 1 or 2%. Okay.
Actually, I have one last
Yes.
question. What do you think about doing fast obstacle avoidance with that? Like
Yes, I have a video. I didn't show it.
I see.
So here what you're going to see, this is in collaboration with a company from Zurich called Insignes.com. That what they're doing is collision avoidance systems for drones. So in this video, you're going to first see the DJI Phantom, which is a commercial product, which has a depth camera for obstacle avoidance. And then in the next footage, you're going to see a video with our drone equipped with an event camera. So let's see what a commercial drone would do with an incoming obstacle. And now our quadrotor with the DVS. Here the algorithm was very stupid actually. It was a very simple optical flow, but the latency was very small, like a few milliseconds. Okay.
And you have and because you also have a very high dynamic range, you're much better.
Yes.
So is it because of the high dynamic range or because
No.
sensing?
No, because of the low latency of the sensor. Here the scene was not high dynamic range. Mm-hmm. Yeah.
What's the velocity it was going at?
3 meters per second or 4. So 15 kilometers per hour. So we are involved in a DARPA project called FLA, Fast Lightweight Autonomy, and there DARPA is really only interested in, mostly interested in DVS technology for low light applications where standard cameras are affected by motion blur and low latency.
Field of view, because one of the things
No.
Like, yeah.
It's like standard cameras. You can
So like
put,
standard
you know,
cameras.
no, you can just replace the lens with another lens.
And that doesn't affect the.
Well, it will affect the angular resolution, but it will
Right.
not have any side effect on the latency or other things, right? Yeah.
Cool. Thank you very much.
Thank you. Thank you.